Welcome to the lecture on Module 3, that is Random Processes of Engineering Statistics and Linear Algebra. Today, in this lecture 7 of this Module 3, we'll see the linear systems. So let's consider the random process that has been passed through a LTI filter, linear time invariant filter. Then the input to the LTI filter is process x of t and the output is another process y of t. Just like in signals and system, we consider a system and its input is assumed to be x of t and output is assumed to be y of t. Similarly, here we are considering an LTI system which is having its input as x of t and output as y of t. The impulse response of the filter we are considering as h of t. So just we can imagine here just like an LTI continuous time system. Here we consider time domain relationships between the input output and input output random processes, and we consider here the x of t is stationary. And we know that y of t is nothing but x of t in convolution with h of t. No need to write, I hope. Y of t is nothing but x of t in convolution with h of t. And we know convolution is commutative. So because of that, we can write this, the integration from minus infinity to plus infinity h of tau, x of t minus tau, the d tau, which is equal to the same. Here tau is the variable of integration. I hope no confusion with respect to linear systems. Now the next point is finding or learning the mean value and mean square value of the output, that is y of t, the output of the LTI system. The mean value of the y of t is given by my of t, which is represented in both of these fashions. It is nothing but expectation of any of these, but we consider this. So it is expectation of y of t is being substituted as this. So once we go for its solution, so y of t is equal to the expectation of the input we are finding. H of t is the system response, or it is the impulse response of the system. So we leave this h of tau, so we go for E of, because with respect to t it is, so it will be fitting over expectation of x of t minus the tau and integration of this. So here E of x of t minus tau is equal to mx of t minus tau, and mean value mx of t is independent of time. Hence mx of t minus tau is equal to mx. Then it is given by my of t is equal to integration from minus infinity to plus infinity h of tau mx of mx h of tau into mx. So we write this as mx. E of x of t minus tau is it is the mean value and it is independent of time, as mx of t minus tau is equal to mx, as it is independent of time. So we can write it as in this fashion. So mx is a constant and we can take it outside, so it turns to this way. We know that integration from minus infinity to plus infinity h of tau e raised to minus j 2 pi of tau d tau is nothing but the frequency domain representation, or it is the Fourier transform of h of tau. So h of tau, the Fourier transform h of tau, if f is equal to 0, then we can write it is equal to h of tau into e to the power 0, which is equal to integration from minus infinity to plus infinity h of tau d tau, which is equal to h of 0. So h of 0 is nothing but this value, so which is same as integration from minus infinity to plus infinity h of tau d tau. So we can write my of t as mx into h of 0, where h of 0 is the zero frequency response of the system, or it is the DC response of the system. Thus my of t is also independent of time, hence my is equal to mx into h of 0. Hence the mean of output process is equal to the product of mean of input process and DC gain of the LTI system. The mean value and mean square value of y of t. The mean value is my of t, and which we have written it as in this fashion, and interchanging this we get in this way as we already obtained this. Next point is the noise. So we are aware of this noise, electronic. Now whatever we are listening to, it is a noise. This record we can see some other sounds. So they are nothing but the noises in this communication. Here the noises are of different type. We are focusing on the thermal noise in this chapter. The electronic components generate thermal noise. The resistance R at the absolute temperature T generates the noise voltage of Vrms is equal to root of 4kTBr, where K is the Boltzmann's constant, T is the absolute temperature in kelvins, and B is the bandwidth of the measuring system, and R is the resistance in ohms. The noise power is given by Pn is equal to V square, Vrms the square divided by R, so which is equal to 4kTB. So from this only this equation for Vrms is being obtained. The average power in random process is given as Rx of 0, because noise is a random process, which will not be, one cannot estimate the amount of noise generated by the system before it occurs. So we consider the noise in this random processes, and certainly the noise is the function of time. The noise is going to vary with respect to time, so we consider this one in the random processes. So Rx of 0 is equal to 1 divided by 2 pi Sx of omega d omega, as it is the frequency domain representation. The autocorrelation of 0 is equal to, at 0 is equal to, we get this value from the previous things. Then Sx of omega is the power spectral density of noise. It has a constant value A from minus B to plus B in Hertz, and let's represent this one. This Sx of omega is given by, like, from B to minus 2B to plus 2B plus minus 2 pi B to plus 2 pi B it is. So Sx of omega is having its amplitude as A and 0 otherwise. Here Rx of 0 will be equal to V square Rms. In other words, Rx of 0 should be equal to V square Rms, which is equal to 4kTB into R. And we can write this one as 1 divided by 2 pi Sx of omega d omega is equal to so much. So the kind of the thermal noise is having a same amplitude over the duration we are going to consider. So the above equation is satisfied. Sx of omega is equal to 2 kTBr. Means when the value of Sx of omega is 2 into k into t into r, then only this equation results this value. So 1 divided by 2 pi into this, so 2k t into r, and we write 2 pi omega, and it runs from 2 pi to 2 pi b to minus 2 pi b to plus 2 pi b, which gives us this equation. So from this We know that the thermal noise is equal to 4 kTB into R, and Sx of omega is given with this amplitude, with this equation. So over a range 2 pi minus 2 pi into B2 plus 2 pi into B, and B is the bandwidth of the measuring system we know. So, and this is the RMS value, that too we are aware of. So from this equation, but the power spectral density is equal to so much. So to equate this, the value of Sx of omega has to be this. By substituting this value as Sx of omega, we are going for solving this power spectral density waveform. So 1 divided by 2 pi integration, instead of minus infinity to plus infinity, because from minus infinity to up till this minus 2 pi b it is 0, so no need to write. So we write it over this reason, which is 2k into t into r and d omega. Omega is nothing but the frequency factor which matters to the bandwidth b. The rest all 4, k, t and r are constants here, and 2 pi from minus 2 pi b to plus 2 pi b, it has been integrated. We take all these constants outside and integration happens with respect to omega. When it happens with respect to omega, we get integration of d omega as omega, and it is 4 pi into b, and divided by 2 pi will cancel out the 2 and 2, and we have 2 pi also, this been cancelled. We get 4 kTb into R, hence the equation. Then the next kind of a noise is white noise. The white noise, the thermal noise generated by the resistance R has a power spectral density Sx of omega, which is a constant function of frequency. That is, Sx of omega is equal to 2 into k t into r, and such a noise is referred as the white noise. And we know that Rx of 0 is equal to 1 divided by 2 pi into integration from minus infinity to plus infinity Sx of omega d omega, and the value of this one is equal to e of x square of t from the previous things. It is equal to del x del square of xt plus mx square of t. Mean value of white noise is 0, hence mxt is equal to 0. So del x square of t is equal to Rx of 0, and that is equal to 1 divided by 2 pi integration from minus infinity to plus infinity Sx of omega d omega. So the value of this variance is equal to 1 divided by 2 pi. The value of Sx of omega will be equal to, Sx of omega is 1 by 2 pi, and Sx of omega we are finding by looking at this waveform. Here it is A. So let's write the value A here. So A into d omega, when we write, we get 2 into A into B. We know that autocorrelation function of power spectral density forms a Fourier transform pair, that is Rx of tau is equal to Sx of omega. The Fourier transform of autocorrelation is the power spectral density. So Rx of 0 is equal to A into omega B divided by pi. So in this equation, when Rx of 0 is been written 1 divided by 2 pi, so when we substitute Sx of omega as A, then the equation would be Rx of 0 is equal to A into omega B divided by pi. Since sine of 0 to 0 is 1, we get this thing, and Rx of 0 is equal to A into omega B is nothing but 2 pi into B divided by this. Omega B is equal to 2 pi B. So this is equal to 2 into AB from the previous equations. So del x square t is equal to Rx of 0, that is equal to 2 into A into B, with mx of t is equal to 0. So this equation, the previous equation, this one and this gives the same result. The width of the main lobe of Rx of tau given by equation and can be calculated as follows. Rx of tau will be 0 when sine of omega v tau is equal to 0, and this will happen when omega t tau is equal to pi, when so tau is equal to pi by omega b, so which is equal to tau is equal to 1 divided by b. So here tau is the coherence time in autocorrelation function and b is the bandwidth of the measuring system. White noise is one which is having its power spectral density constant, means which resembles this structure but which will be having this power spectral density as constant. And now here in case of this noise also the power spectral density remains constant, so this can be referred as a white noise. So even though the thermal noise it is, even it can be referred as the white noise. So we are learning the thermal noise and white noise in this lecture, and the value of the tau is pi divided by 2 pi into b, and tau is equal to 1 divided by 2 into b here. So it is running from minus tau to plus minus 2 pi 2. So this is the end of this lecture. We know what is the difference between white noise and the thermal noise, and let's see the further things, if any queries are there, those things in the next video. So thank you for watching.